Hello, how's it going? So in my previous video that I made where I was talking about low-level Python, somebody made the comment that that was the coolest C with extra steps that they'd seen. And I thought, let's have a bit of fun. Let's just do something really weird. So what I'm going to do is I'm going to make a simple program that emulates a computer, all the internal components. So I'm going to start with the specification. Let's just sort of describe our imaginary computer. Computers have registers, and registers sort of store intermediate values. So let's just say I'm going to give myself 4 registers. Okay, so any of these can store values, and I'm going to make them all unsigned 64-bit integers. And I'm going to have another register, which is my program counter. And what my program counter is going to do is it's literally going to track which instruction my program is currently looking at. Speaking of instructions, I'm going to keep it really, really simple. I'm going to have 4 instructions. Okay, so one of them is add. I'm going to add from, store the result in some destination register, and I'll go ahead and add the contents of 2 other registers. Then I'll have an instruction to load from one source register into a destination. Then I'll have an instruction to load an immediate value. That's literally just like a literal value, like 1, 2, 3. And the last instruction, I'm going to be able to do a syscall. So, alrighty. So this add, load immediate stuff, this is all just sort of dealing with registers. System calls are going to be interfacing with the rest of the operating system. I'm just going to use my regular operating system for this. But in order to do that, I'm going to have some sort of calling convention. Because with computers, when we make a system call out to the operating system, we usually do that by first up loading in a number to one of the registers, which is the function number that we're going to call in the operating system, and then loading in some other variables to the other registers to store the parameters, and then that call happens and another one of the registers, the return value, is stored in there. So my calling convention on my machine is that R1 is going to be the function number that I'm calling. R2 is going to store the return value, and right now, because I'm keeping it really simple, I'm only going to take one parameter, and I'll put that in R3. Okay, so now what I'm going to do is I'm going to just write a really simple program that uses these instructions. So I'll just go in and I'll have call it program dot whatever, but just to be cool, I'll make it .asm. So what I'm going to do is I'm going to, let's start with this. Let's load in the immediate values 42 and 13, add them together, and then print that out to the screen. So we'll load an immediate into, into R1, 42, and then load into R2, 13. Then I'll add, store my result in R3, and I'll add register 1, register 2. Then what I will do is because I'm going to do my system call now, so I'll just say that, we should have this as well. We should have system calls. Right now there's only one of them, that's the print function. Okay, so I'll load in number 0 to indicate that I'm about to call the print function. Then I'll do a syscall. And that'll be it. So that's my program that I'm going to be running. Okay, now let's get to actually making this stuff. So to keep things nice and simple, I'm going to deal with NumPy arrays, at least for my registers. So I'll just declare the storage. We'll have 5, that's the 4 general purpose plus the program counter. And those will be 64-bit unsigned integers. Great. And I'm also going to have a register lookup dictionary, which defines, well, for every register name, where is its address in the register. Now don't worry, I'm not going to be doing this at runtime. This is just for compilation, where I sort of ingest all these strings and then print them out, turn them into some meaningful things. Anyway, so as my keys, I'll have the register names, and as my values, I'll have their location within the array. So that's all well and good. Now what I'm going to do is I'm going to write a few other helper functions. First of all, to sort of validate. So as I'm reading along here, I'll be reading out these bits as strings. I want to sort of grab them and have a function that quickly tells me whether that's a valid register label. And then I'm going to have a function which parses. So it takes in that register label and returns the actual integer location. So luckily we have this register lookup dictionary, so we can just return whether the given word is in that register dictionary. And then when it comes time to parsing that register, I can assume that the register is valid already because I've got a different thing, I've got a different routine to check that. So what I can do is I can just return the register lookup entry matching to that word. Okay. Now while I'm at it, I'm also going to make some functions to deal with integers because, right, I've got these immediate values coming in, so it would be good to be able to check those. So again, I'll be able to check if I've got a valid integer. And this one's a little trickier, but there are two cases. One case is when that word is a digit, and that means that all the characters in the word are digits. But then there's another case, and the other case is if that word starts with a minus. So I'll say, okay, we have word element 0 being minus, and the rest of the word, so from position 1 onwards, is a digit. Okay. Now in terms of parsing an integer, this is not too bad. All we need to do is convert that into an int. Cool. Okay, so now I'm going to basically do the same thing for each of my instructions. So I'll have an instruction to, first of all, perform an addition operation, then secondly, to validate, to check whether a line that I've been given represents a valid integer operation, and last of all, to actually parse that integer operation. Now, that seems a little strange. What I mean by this is when I get, let's say add for instance, when I throw in this line and I say, okay, I've already checked this, this is a valid add line, can you give me a list with all of these things here? I hope that makes sense. Anyway, you'll see where I'm going with this. So like I said, first of all, I'll have to define a function to perform that addition. And that addition will take in, all of these will take in a list of integers, that's the data, the operands, and they will return nothing. So what I'll do is, first of all, I'll grab these, so I'll get the destination. And then I will go ahead and do this. So this is all dealing with registers, right? So we get the destination register will be the sum of the contents in these two source registers. And then we're done. Now, while I'm at it, I'll just go ahead and I'll duplicate this a little bit, because a lot of these are sort of the same. So I'll have load immediate, and syscall. Now syscall is a little bit different, but hey, we'll cross that bridge when we get to it. So where was I? Load. Okay, so load goes, get the source, put it in the destination, and here's how we implement that. Okay, load immediate does the same thing, except instead of a source, we just have an actual integer value. So what we can do is directly just say, store that direct immediate value into the appropriate register. Alright, so syscalls. This is a little bit strange. So what I'm going to do is I'm going to say syscall our lookup table. At the moment we just have the print function, so that's the one and only. Yeah, I mean that's the one and only thing that we've got. So when we perform the syscall, we'll say, let me say result is given by, we go, grab the appropriate syscall lookup. That syscall lookup, remember, the system call number is always in register 1. So we go ahead, we call that function, and the argument that we provide is stored in register 3, if I remember correctly. And the reason I'm storing this in an intermediate result is usually these things would sometimes return void, sometimes return 0, stuff like that. I want to check if that result is none, then let me do this, I'll return. Otherwise, we'll go register register 2, that's it. Gets that result. So at the moment it's always going to be returning because print returns none. This is like a function that returns void. But yeah, so hopefully you can see that although this is a little bit strange, this is going to basically implement all of these methods. So what I'll then do is I'll then worry about validating these things. So I'll say, all right, how do we check if we've got a valid add operation? What I'm going to do is I'm going to take in words, which will be a list of strings, and I'll return true false. Okay. Alrighty. So I'm going to assume that the opcode has already been checked, so I already know that I've got an add instruction. One thing that I need is I'm going to check the number of elements that I've got in that list of words. So I'll say if the number of words that I've got is less than 4, then it's invalid, we don't have enough there. The reason I'm saying less than versus not equal, right, because right here I've got 4 words, I could also have some comments on the end, you know, put a comment there. So I want to allow for that. Okay, so now what I'll do is I'll check, so I'll check if if words 1 is not storing a valid register, then we'll return false, and I'll do the same for all the other ones. So this is the checking the source, and then destination, then source 1, then source 2, those all need to be registers. Okay, now let's go and have a look at loading. So for loading, we've only got 3 arguments. We have the opcode and then the 2 operands. So we need at least 3 words there, and these other 2 need to be registers. Okay, now for load immediate, it's a little bit different. Because word 1 needs to be a valid register, but word 2 needs to be a valid integer. Okay, now as for validating syscalls, well, that's quite a bit simpler. The only thing I need to check is the number of words, because the syscall is just going to have the operand, the opcode. So I just want to check that we've at least got 1 word in there. Okay, right, so let's have a look at, parsing an add instruction. Well, what we're going to do is we're going to take in that line again, which represents everything, and we're going to return a list of integers, which is just storing the data. So like I was saying before, in the case of a register, we want to look in and fetch the appropriate register number for this code. For an immediate value, we just want to turn that into an integer. So in the case of an add function, we're just going to pass all of these as registers. Just like that. Then in the case of a load, very similar, except just two registers there. And then in the case of load immediate, we will just take in that second word as an integer. And a bit of a trick here for the syscall. Because the syscall doesn't actually have any operands, it's just that, right? Nothing. That's okay. That's fine. Okay. So now what we've got is we've got rules for parsing and validating all of these codes, and it's time to start putting all of that together. So the way I'm going to put this together is a compiler engineer might call this a system table, a symbol table, sort of. I'm just going to call it opcode lookup, because assembly is quite a bit simpler than compiling. So what I'll do is I'll have for the keys of the dictionary will be the opcodes, and then the values will be their own lookup tables. So for all of these, we'll have an address, which is the function that we're going to call, and then we'll have another function to validate that opcode, and then we'll have another function to parse that opcode. And I'll go ahead and I'll use that for all of my operations. Cool. So hopefully you can see how these functions are being linked to by the opcode lookup. So the way my virtual machine is going to work is I'm going to have a list of just the instructions. Those are the function pointers that I'm going to call. Then I'll have another list with the arguments for all the instructions. I probably could put that together, but I just don't feel like it. So what I'm going to do is I'm going to make a function that will basically load in a file and convert it into the data structure that I need. I'm going to take in a set of instructions, that will be some sort of list, and a set of data, that will be some other sort of list, as well as a file name. Okay. Now the first thing I'm going to do is I'm going to clear all of my stuff. Because although I will probably only call this once, I want to just make sure I'm doing it, the right way. Alright, so the first thing I'm going to do is I'm going to open my file in read mode. Then I'm going to read all of the lines. Just to help out, I'm going to include a line number so that if something fails, I can give back a compilation error and say, hey, there was an error on this line number. Okay, so first of all, I'm going to get all the words. So I'll take that line, I will strip out all the new lines and everything, and I will split that around the space. Then I'll grab the opcode, and I'll check this. So I'll say if that opcode is not valid, then I will just look at the next line. So this is going to handle, again, cases where we've just got comments. But I just noticed this. I should probably... let me do this. I'll start at line 0 and then I'll always increment my line. That way I don't need to worry about incrementing it in all of the continue cases. Okay, so I'm going to define another function that will tell me whether an opcode is valid. Okay, now this is starting to get like a little bit of fun, because what I can do is I can go into my opcode lookup, put in my my opcode, and that gives me that second dictionary where I have access to function pointer, valid, and parse. And in particular, I want to check whether that is valid, put in the words, and that will call that function for me. So over here I've got an opcode, so what I can do is I can say, well, if it's not valid, then I can print out a compilation error. So what this will do is this will print out the line number as well as that exact line where that error occurred. So what I can do is I can add in the instruction pointer, the function pointer. So I'll append to my set of instructions, and what I will append is if I go in and get the appropriate function pointer. That'll be in there. And then I will, if I go, get that, whoops, get that opcode, and then get the parse function for that instruction, call that, put it in the words, that should give me back a list. Okay, so this all seems a little abstract at the moment, but what I'm going to do is I'm just going to make a function that will go through and basically do a binary dump. So it'll print out like all of the stuff that I've got in those instructions and data. So what I'm doing is I'm just looking through and I'll get the instruction and the set of arguments. And then I'll just print it all out. So I'll print out the line number, then the instruction, and then the arguments. Okay, so let me just, we're getting somewhere. We are getting somewhere with this. Here's the state of my machine, and I'll go ahead and load that program. And then I'll just do a binary dump of that program. And fingers crossed, let's see what's happening. Aha, nice. Of course we can't do that for this in instructions, no way. Okay, very cool. Let me just get this, make this visible. So yeah, you can see that, you know, for every line, we've got, you know, the appropriate line number is coming in, and then we see that we have turned these opcodes into actual function pointers that we can call at a later point, and we've also got the register number over here, for instance, and the number that we are loading into that register. And we can see all this stuff, it's all working. Okay. So surprisingly, we are like almost done with this. So the way a program operates once everything's loaded in is we just keep working with the program counter. So element 4, I believe, is my program counter. So while we've still got some instructions left, we'll keep going. Every time after we do our instruction, we will increment our program counter by 1. And then what we'll do is we'll look into our instruction set at the program counter position. We will call that function, and the arguments that we'll put into that function are the, that set of arguments, same program counter location within the dataset. So again, you can imagine it as right on the left here is like a big array of function pointers ready to be called, and then on the right, an equally sized array of sets of parameters ready to be put in there. And then the program counter is just incrementing, and doing its thing. All right. So I'll just run that. Was that the wrong number? Whoops, register 4, not register 5. Okay. Right. What's going on here? My bad. What I did is I put in the wrong register number for the parameter for the syscall. So this should be actually, off by 1 error, right? Because R3 is going to be register location 2, R2 is going to be register location 1. All right, so there we've got it. Nice. Okay, yeah, so we've got that binary dump, that all comes in, and then we add 42 and 13, so R3 is then storing 55. We set the print function number, we do a system call, and that goes in and prints R3, which is 55. Okay, let's have some fun with this. So let's make a program that keeps counting up forever. So I'm going to put 1 in R2, because I'm always going to add 1. Then I'll go ahead and increment. I'll do that system call. And then after I do that system call, I'm going to load the contents of R3 back into, wrong order. I'm going to load into R1, I'm going to be putting back the contents of R3. And then what I'll do is I will load an immediate value into the program counter, and I want to go back to this line here, so I'll set the program counter back to location, off by 1 error, right? Back to location 1, that will put it on line 2, and remember that the way this works is immediately after loading, the program counter gets incremented by 1. So that will bring me to the start of line 3, and we'll add 1 again. But let's test this. Nice. It's going on maybe forever. Cool. So there we have it. This is just a bit of fun, because it is fun to learn how computers work. Yeah. Anyway, so in this video we sort of this is just like a fun afternoon project, just sort of mucked around, defined our own instruction set and virtual computer, compiled an assembly program written in our instruction set into a data structure that Python can understand, and executed it. Okay, so I hope you had fun, and I'll see you again soon. Bye.